In this video, I'll provide a quick start guide for the Object Attributes Baker tool, part of my Game Tools Blender extension. The name might sound a bit cryptic, but it's essentially Pivot Painter, just rebranded. I've reworked some of its features to enable new workflows that are no longer tied to Pivot Painter specifically. At its core, it's a tool that lets you bake object attributes, including hierarchy information, along with a way to traverse from parent to parent, reconstructing a hierarchy just like Pivot Painter does. So in this video, I'll walk you through the classic Pivot Painter example. Here's a very simple test scene. We have a trunk, a branch, a secondary branch, or let's call it a twig, and a leaf. All object transforms were applied on purpose, just to show how easily pivots can be adjusted in Blender using a few handy tools. First, I'll go ahead and enable the Origins toggle. This allows me to move each object's origin independently without affecting the object's position in the scene. Alright, starting with the trunk, its pivot is fine as is, since the object is centered at the world origin. I just want to adjust its orientation. I'll set the z-axis as the up axis and the y-axis as the rotation axis that I'll be baking. This is an arbitrary choice, it doesn't really matter as long as you stay consistent and choose based on your end goal. Same idea for the branch, but this time I'll reposition its pivot by pressing G, like that. Again, the z-axis should follow the general direction of the branch, and for the y-axis, something like this will do just fine, I suppose. I'll repeat the same process for the twig and the leaf. Great. Now I just need to parent everything. Leaf to the twig, twig to the branch, branch to the trunk. Let's double check that everything works. I'll disable the Origins feature and rotate each part. Check, check, and check. Okay, next I'll select all the objects and locate the Object Attributes Baker in the Game Tools sidebar. If you're just after the default Pivot Painter setup, you can apply the provided template directly. But for this video, I'll go through each step manually. I'll start by creating a new texture and naming it Pose Index, whatever. Each texture needs a unique name. In the red, green and blue channels, I'll store the object's position, mapped to X, Y and Z respectively. In the alpha channel, I'll store the hierarchy index and set the depth to 1. This stores the index of each object's immediate parent, which we can later use in the shader to walk the hierarchy from child to parent. Now I'll create a second texture called Axis Extent. In the red, green and blue channels, I'll store the y-axis direction mapped to X, Y and Z. In the alpha channel, I'll store the extent along the z-axis. And that's pretty much it. I'll use the Pivot Painter algorithm for encoding indices, and limit depth can be disabled. In the mesh panel, I'll name the baked object. Then I'll save the blend file to unlock the export settings and set the export path. Same goes for the textures. The default size of 256 cubed should be more than enough. It can handle up to 60,000 elements, which actually exceeds what the Pivot Painter algorithm is capable of encoding. You're unlikely to exceed this amount of objects anyway. I'll set the texture export path and hit bake. Let's double check the generated UV map. Since there are 4 elements, a 2x2 texture is indeed enough. All the vertices of each object are centered on a unique texel, so everything looks good. Now let's jump into Unreal Engine. I'll import the FBX without any special options. I usually like to disable everything to keep things clean, just make sure Combine Meshes is enabled. Inside the Static Mesh Asset Editor, I'll make a few adjustments. Distance field may need to be disabled, depending on the kind of vertex animation you plan to apply on this asset. Light map generation may also need to be disabled, or at the very least, make sure it doesn't override the generated UV map. Nanite likely needs to be turned off as well, since it can interfere with UVs and doesn't play nicely with vertex offsets. 32-bit UVs are probably not required for the workflow we are demonstrating today, although some other, less common setups might need them. No need to worry about that for now. Finally, you may need to offset the bounds to accommodate vertex displacement, depending on the type and intensity of motion you plan to drive in the vertex shader. Alright, that's it for the mesh setup. Next, I'll import the textures. Set both to HDR 16-bit and compressed, and change the filter mode to nearest. Now let's create a material. Drag and drop the two textures into it and convert them to texture objects. Create a material function node and search for the function named mf_pp_getFirstLevel. These functions are included in my content examples project, packaged as a plugin you can easily copy over to your own project. Connect the UV map, usually UV index 1, as reported by the bake tool. Then plug in the texture storing position in RGB and indices in the alpha channel. This function outputs the element's own index derived from the UVs and texture width. I recommend using named reroutes to keep things clean and readable. For example, level1_index, level1_UVs. Now copy and paste the material function again and search for mf_pp_getExtraLevel. Plug in level1_index as a self-index and level1_UVs as a texture UV, and connect the same texture object. This function assumes indices are encoded using Pivot Painter's algorithm by default, which they are in this case, so decode is enabled by default. And you usually don't need to worry about 8-bit decoding. Again, create named reroutes for this new level. Level2_index, level2_UVs, level2_child. Repeat the same process 2 more times. Use mf_pp_getExtraLevel, wire in the previous level's index and UVs, and connect the texture. Create named reroutes for the level 3, and then once more for the 4th level. Now, we need to compile these UVs into actual sampling UVs using a dedicated function. Feel free to use reroutes again for readability. The logic behind this function is thoroughly explained in the material function itself and in the wiki, so I'll skip the technical breakdown here. This is not a deep dive into the Pivot Painter algorithm. I already did that a while ago anyway. Today's video is just a quick start guide for the tool. Alright, now we can get cooking. We'll sample the position/indices texture 4 times, once at each depth level. I'll fast forward the process of wiring those and creating the corresponding named reroutes. Then I'll repeat the same process for the texture storing axis and extent. Now I have everything I need to start manipulating vertices in a way that mirrors the hierarchy we set up in Blender. It's not super straightforward, so bear with me. First, I'll create 8 named reroutes to represent the rotation axis and angle for each level: leaf, twig, branch, and trunk. For each axis, I'll just forward the axis sampled from the texture. For the angle, I'll keep it simple for now, using 4 scalar parameters, each multiplied by a mask corresponding to its level. Now let's apply these rotations hierarchically. We need to process them in reverse order. First, rotate the leaf around its own pivot point, then rotate the twig, which also affects the leaf, around its pivot, then the branch, and finally the trunk. If we were to rotate the trunk first, the pivot for the branch would be moved as well, making it harder to apply subsequent levels of rotation as the pivots would no longer match what's baked in the texture. Doing things in reverse lets us use the baked pivot positions as is. So I'll rotate the vertex local position. The pivot point comes from the depth 4 pivot. Rotation angle depth 4 angle. Rotation axis depth 4 axis. Now, the rotate about axis node outputs an offset. But that's not what we want here. We want the actual rotated position. So we'll simply add the rotation offset back to the original position. I'll repeat the same process for the twig, level 3, the branch, level 2, and finally the trunk, level 1. Only after all rotations are applied do we convert the final position to an offset by subtracting the original position. And since we are working in local space, we'll need to convert the result from local to world space before plugging it into the world position offset pin. And voila! If I tweak the rotation amounts, I should see a proper hierarchical rotation. Rotate the trunk and everything rotates with it. Rotate the branch and the trunk stays put while the branch, twig and leaf follow. Really cool. Now we still have one task left, fixing the normals. Fortunately, this is super easy since most of the setup can be reused. Instead of rotating the local position, we'll rotate the local normal. And because a normal is a unit vector, it should be rotated around the origin, 0, 0, 0. Unlike with the world position offset setup, the final rotated normal should not be converted to an offset. It should be used as is. However, it's recommended to normalize the result and pass it through a vertex interpolator to avoid performing expensive trigonometric operations per pixel. Per vertex is already costly enough. Finally, convert the normal from local space to tangent space, assuming the material uses tangent space normals, which is typically the case. And voila! From here, the sky is the limit. Let me give you a quick overview of a very simple setup. To keep things straightforward, I'm still using the rotation axis directly from the texture. The rotation angles for each level look a bit more complex, but it's pretty simple. Each one is just an oscillating signal. Time is multiplied by a scalar to slow it down. Amplitude is reduced significantly. Remember, a value of 1 corresponds to a full 360-degree rotation, so you'll want to keep values small. Then, for each level, I simply offset time based on the distance from the vertex to its pivot. Specifically, the distance from the vertex to its pivot divided by the baked extent along the z-axis. So a vertex near the tip of a leaf will get a value close to 1, and a vertex near the pivot will be closer to 0. Same goes for a twig, branch and trunk. The further away from the pivot, the greater the time offset. And that's a simple way to create a kind of delay effect along the mesh's length. Too much delay and it looks off, but just the right amount adds a nice sense of weight and momentum to the animation. Really simple, right? And voila, like I said, the sky is the limit. You could take this much further, like Epic did back in the day with their hill tree example. I've completely reworked that example from scratch to make it clean, modular and easy to study. Perfect if you want to dive deep into its inner workings.